This is some work that I've been doing the last few years is looking at something different. I mostly work in the Appalachians, but looking at different older rocks around North America. And when we look at North America, it's a very unique continent. It's unlike any other continent on Earth, because when we look at, this is Hank Williams' diagram, the core of North America is cored by an Archean craton that's surrounded by younger and younger orogens. This was the first recognition 200 years ago for geosynclines, and that new mountain belts always form adjacent to old mountain belts. And we see that everywhere in North America, and it's kind of an annular system like tree rings where the continent builds out and out and out. We don't see this anywhere else on Earth. Tuzo Wilson recognized this in 1963, not in the Appalachians, but in the Archean cratons, where he first came up with the idea of mobile plate tectonics. And we now recognize this as representing Wilson cycles and supercontinent cycles. If we look closely in eastern Canada here in this region around the Labrador Sea, it's kind of unique because the North Atlantic spreading axis bifurcates at a triple junction, separates Greenland from the rest of Canada, and creates this nice cross-section into the continent where we have two Archean cratons, the North Atlantic and the Superior, and then a successive orogens, at least four, that kind of build out from that. The Torngat and Makavickian in the Proterozoic, the Mesoproterozoic, Neoproterozoic, Grenville, then the Appalachian origin on the edge, and then all of these are surrounded by the Atlantic Mesozoic, the modern margin. And this sort of orientation we don't see anywhere else really on Earth. If we look closely at the Labrador Sea records that breakup and separation from Greenland. It formed as a triple junction in the Atlantic where we had seafloor spreading. It's a magma poor margin in the south, but a magma rich margin when we get to the north in the Davis Strait, and records that asymmetric breakup. It has an extinct ridge that runs down its center, and it had a reorganization in the Eocene, which is accommodated by a bunch of transform faults and now modern fracture zones in the origin. So the question to look at really is, what controls rifting in new oceans, especially in this area? And I don't think it's entirely fortuitous that new oceans form on old mountain belts. It's been long recognized. But what is it that controls that? It's something in both Wilson cycles and supercontinent cycles. It has to be structures in the lithosphere. And there's really two kind of ideas of thought on that. Do we see these controls in the brittle upper crust? This is Bill Thomas's model, looking at modern rifting in the Atlantic and how features in the Atlantic sort of parallel old features in the origins, suggesting that the upper crust plays the dominant role for how we break apart continents. And then opposite of that are these controls held in the mantle. This is Alex Peace's model from the Davis Strait. The difference for this is it's very easy for us to sort of see the upper crust. We can observe it, study it, whereas the mantle gets more difficult. So how do we study the mantle? Most of it's done by computer models, and they're great, but they have limitations based on computing power and human imagination. So really, if we want to look at the mantle, we are going to look at, say, mantle xenoliths and rocks, or at least in eastern Canada, we see the world-famous Bay of Islands ophiolite, the complete mantle section here back behind the town of Woody Point. And then when we get up close, we see these peridotites, these olivine-rich peridotites, the fabric that's held within them. But the issue with using this to look at modern mantle is that this is Ordovician mantle. We look at these peridotites lie just below the Ordovician moho. So it's, how does that mantle change through time? So the other issue with this is that mantle rocks and ophiolites are very limited on Earth. So it's a space and time issue. So how do we study mantle deformation? And one way we look at this is we use earthquakes. And rather than just looking at surface waves, very specific body waves of teleseismic body waves, those waves that travel over 1,000 kilometers through the Earth. And there's two main types, SKS and SKKS. So an SKS wave transits through the mantle as a shear wave or an S wave, enters the core where it's converted into a P wave or compression wave, and then reemerges into the mantle as an S wave where it's recorded. An SKS wave is very similar, except it reflects off the core mantle boundary as another P wave and then reemerges. And this is key because what happens when these waves emerge from the core is that they become polarized. They're plane polarized in the direction of travel. That P wave converting back to an S wave becomes polarized. And we use that polarization in the wave to give us information about what's going on in the mantle. So if we look at a polarized seismic wave here in this animation, when it hits an anisotropic material, that wave becomes split, and it splits into a fast wave and a slow wave. The exact same as property we use with light to identify minerals. Essentially, seismic waves are birefringent like light. And we use that separation of the two waves to give us two bits of information. We calculate the direction of the fast wave, essentially this blue plane through here. We can measure that, and we measure the time difference, or the retardation between the fast and slow. Because they're travel dependent, their time and their velocity is dependent on the direction they move through the medium, they will have a retardation in time. We can measure that difference in time to give us information about what's going on inside the Earth. So if we apply both of these bits of information to Eastern Canada, we look at the anisotropic measurements, the direction of the fast values measured on seismograms all tend to dominantly parallel the east-northeast direction as the main structural trend of the orogens, both the Appalachian and the Grenville. And there are several reasons for this. The most obvious is this related to present-day flow or direction of plate motion? And the absolute plate motion of North America at present is northwest directed at 23 millimeters per year. So it's at a high oblique angle to what we're measuring here for our fast directions. So it tells us that that source of the anisotropic source is in the lithosphere and not in the asthenosphere. And the second bit of information, we look at those delay times. They're average around 1 second, which is too great to be a source in the crust. That time difference tells us that that anisotropic source lies beneath the MOHO, but above the asthenosphere. So both bits of information tell us we have a foliation that's east-northeast directed, parallels the strike in the origin, and it lies beneath the MOHO, above the asthenosphere. It is in the lithospheric mantle. And the reason for that is olivine. Olivine is one of two minerals that comprise most of the mantle, perovskite being the other. But olivine is key because it is seismically anisotropic. It has its fast axis down the A-axis of the mineral. And so in this case here, if we have randomly oriented olivine, it is isotropic. It will display no sort of preferred orientation. But if we deform that olivine in the mantle, the olivines align. We align those fast axes, and we develop a planar feature that we measure in seismic velocities. And where we see this in the mantle, we get seismic anisotropy in the crust in the upper mantle. We don't see it in the lower mantle because it's mainly composed of perovskite, that calcium titanium oxide, which is not seismically anisotropic. We pick up anisotropy at the D prime layer and in the inner core, but mostly we use this seismic anisotropy to tell us about really the upper period or upper surface of the Earth. And if we apply this to how does this relate to geological features? Well, the most obvious, probably the largest, both spatially and in time, geological feature perhaps on Earth is the Charlie Gibbs fracture zone. It has been existing since the Jurassic when the Atlantic opened. It's a fracture zone that starts on an active transform fault that offsets the mid-Atlantic spreading ridge, and it extends right across the ocean to both continental margins.
You're now at 11 minutes.
Okay, thank you. It comes ashore. We're going to look at here what happens when it comes on at the Atlantic margin. Well, it terminates at the continental margin here at a rift transform offset formed by opening the Atlantic, and it terminates right along and aligns with the Dover Fault through here. And the Dover Fault is key because it is one of the major structural boundaries in the Appalachians. It's a big sinistral oblique tectonic junction. It is the collision of the Pyrigondwanan microcontinent of Avalon to composite Laurentia. It penetrates the entire lithosphere into the mantle. It has repeated motion over a 45 million year period, and it has a classic stitching Pluton, the Ackley batholith here that records its final juxtaposition. This is a picture of the town of Dover showing that fault right through here as it continues right down the bay. So it is one of the major features. We move north into the Labrador Sea. We see a similar alignment. The Menai Fault Zone comes to the Cartwright Fracture Zone. It comes ashore at an offset on the continental margin, and it aligns with the Grenville Front. And the Grenville Front being the largest feature of the older Neoproterozoic Grenville origin, a Tibetan-style long, hot origin. And that front is the thrust boundary that marks the northwest limit of transported rocks in the Grenville. Like the Dover Fault, it penetrates the entire crust right down into the upper mantle. So it's a major tectonic boundary. We look at other boundaries in the Appalachians, such as suture zones and faults. We see that none of these features they're active in the Paleozoic, but they have no sort of any renewed motion in the Mesozoic, including big faults like the Cabot Fault in Logan's Line. And the reason for this is that these features record collision on essentially intra-island arc terrains. This is Case Van Staal's model through here. So these brittle crustal structures have no sort of controlling factor in rift offsets. We don't see any sort of motion after the Paleozoic. And we see the same thing when we look at our Atlantic rift basins. The Mesozoic basins all form on reactivated Paleozoic faults. Yet, they terminate at the ocean-continent transform or ocean-continent boundary. When we look at Iapetus rift structures, the Lake Melville and the Sandwich Bay Graben, they're at a high angle to other Iapetus rift structures, the Saguenay Basin and the Ottawa Basin. So in all of these features, we see that these faults do not penetrate the entire crust in the third dimension, and they do not extend past the ocean-continent transition. So they are rift features that are held in the crust and the crust only. So what is it about the Dover Fault and the Grenville Front that makes them unique, where we see their extension transverse into the modern ocean margin? And what's common to both of them is that they are both related to episodes of orogenic collapse. Both the Grenville and the Appalachians, or any mountain belt, origins are zones of weakness. They have structural weaknesses in the rocks, low viscosity layers at their base. They're composed of continental lithosphere, which is quartz-rich and is ultimately weaker than oceanic lithosphere. And this is Platt and England's model from John Dewey's 88 paper, showing that once we extend the lithospheric mantle, we will uplift mountains and then gravity will force them back down. And so how does this relate to both the Dover Fault and the Grenville Front? Well, this is Toby Rivers' model of Grenville orogenic collapse along the Grenville Front, the structural model, and then Aphrodite Indaris and her students who demonstrate orogenic collapse based on metamorphic core complexes and high pressure metamorphic rocks, and relating their uplift to rapid collapse. And we see the same thing in the Appalachians. And the advantage in the Appalachians is we have supercrustal rocks, and we have all the features that indicate orogenic collapse. This is Case Van Staal's model for slab breakoff, is reducing that mantle lithosphere, and then Hillenbrand's model of the Acadian altiplano. So we have evidence on both origins for a late-stage orogenic collapse. Well, how does this preserve a mantle fabric? Well, if we look at where the strength of the mantle is, or the strength of the lithosphere. Prior to uplift, we have essentially a weak crust and a strong mantle, and a very weak lower, mid to lower crust. So we have two strong parts with a weak interior. Most of the strength is held in the olivine-rich mantle. And then after collapse, when we uplift the moho, we sort of bring that strong mantle above the brittle ductile transition as we thin the crust. But what we do is then we strengthen that upper mantle. It undergoes retrograde metamorphism and isobaric cooling. The strongest part of the lithosphere is the mantle. So we essentially freeze that mantle fabric in place as we uplift the mantle. And we see this if we look at yield stresses of sort of rock strength and gravitational potential energy. Prior to collapse, we put the crust in tension as the gravitational potential energy is held in the high mountains. We can't thrust those mountains as we continue to collide above 3 kilometers. So we broaden them out. We transition from a tension to a compression in the crust. That's how we make, say, the present day Tibetan plateau. And then following orogenic collapse, we uplift the mantle. The gravitational potential energy is transferred into the mantle, putting the mantle into extension. The strongest part of the lithosphere is in the mantle. So even though the rocks in the crust break because it is weak, the controlling factors are held in the mantle as it's put in extension. So if we look back to the Labrador Sea area, we have both the Dover Fault and the Grenville Front that extend into the modern ocean. But if we go north, we see the same sort of pattern here in the Snorri fracture zone and the Kanariktok shear zone. This is a major Paleoproterozoic collisional boundary at the Makovikian origin. It has a later episode of extension and strike slip reactivation, massive granite plutonism. And we go north again, we see the same sort of alignment in the Hudson fracture zone. Its trace aligns with a Neo-Archean suture, the collision between the Hopedale and the Saglit block. And then even further north, we see the Ungava fracture zone opening of the Davis Strait comes ashore at the tectonic boundary between the Archean craton and the Torngat origin. It has possible evidence of extension in the massive Hutton anorthosite. So we have at least 5 modern fracture zones in the ocean that correspond to old tectonic boundaries in the North Atlantic continent through here. What's key about them is that where they come ashore, they're always at rifted offsets and they always have basement high. The Cartwright Arch, the Oak Arch, the Lady Franklin High, and the Orphan Knoll. And so what's unique about this is how long tectonic memory persists. The Labrador Sea is unique because that ocean doesn't parallel old oceans. It cuts them at 90 degrees into the continent. So we don't see this elsewhere. And so I guess the last takeaway, what are the keys that we see of tectonic memory, is that inheritance in the modern crust occurs on both old and young tectonic structures. So that mantle fabric must exist through multiple Wilson cycles. And even when we look at today, the Labrador Sea continuously, it's a weak zone. It has earthquakes that continue to this day. The thickness of the crust is clearly not a factor in how we rift, because the crustal thickness varies underneath the Archean cratons out to the modern Atlantic margin at the Grand Banks. These observations state that probably modern style plate tectonics must have existed since at least the Neo-Archean. So it perhaps gives us a time rate for when plate tectonics began. And it really ultimately is that the modern ocean crust and its geometry and the features within it were determined by tectonic events in the Archean. And I guess that's the last point I want to make on this. It's kind of, we think of how the modern crust could be influenced by Archean tectonics. It's kind of impactful. So that's all I have to say, and thank you very much.
Thank you so much, Jeff. We are at time. There is a question in the chat about disentangling lattice preferred orientations and cracks and things like that from seismic anisotropy. I'll leave that to you to answer because it looks longer than we can do in the next 2 seconds. I guess my one question for you, very briefly, is with respect to the shear wave splitting that you have for Labrador. There's not a lot of measurements there, but there are more stations up there than have actually been analyzed. Is that something that you would see as a future thing, as just pummeling way more stations up there along the coast to confirm that?
Yes, that's the limitation of this, is there are very few measurements from this, and they increase rapidly when you get into the US from Earth scope. And I think
Right.
we need more of these, mostly in Eastern Canada and Northern Canada. The limitation of all of this is the amount of data. It's just we need more data in the
Indeed.
Labrador Sea and really in Greenland on the opposite margin.